so far, right. So, we have been making an assumption that the agent is operating in some kind of an MDP, right, and then we are learning policies for trying to solve it optimally and so on and so forth. So, one thing is that we assume that at every point of time the agent has access to the full state information. The agent knows exactly where it is in the state space, and we had assumed that the state space is Markov, right. So, and as long as the agent knows where it is in the state currently, it has sufficient information to make decisions. So, did we violate it at any point of time? The assumption that the agent knows exactly where it is in the state.
State parameterization.
When we are talking about value functions and stuff like that, right. But if you think about it, we still assume that the agent knows where it is in the state space, except that when it looks up the value function, it looks it up in a parameterized form, right. But still the agent was aware of where it was in the state space, and then it just looked it up in a parameterized value. It is not like the agent did not have information about where it was in the state space. At all times we assume that the agent knew where it was, right. So that is the crucial assumption we have made all along, right. But it turns out that such an assumption is often not valid in practice, right, because of a variety of reasons. So, there was one instance where I did in the discussions, right, we did violate this whole knowing where you are for sure thing, right. I mean, remember we are talking about state space here, right. So, when we talked about hierarchies, so there was an instance where we actually were willing to give up information about where we are exactly, so that we can learn more compact policies, right. I was telling you, if you have to, when you are solving the navigate problem, you do not really care whether the passenger is in the car or which one of the RGBY locations the passenger is in, right. You just want to navigate to reach there, right. So, I do not have to worry about the passenger location, nor do I have to worry about the passenger destination. In fact, I gave up information, right, so that I could have a more compact representation for the navigate policy, right. It is easier to learn and so on and so forth. So, in some sense, even though I gave up on knowing exactly where I am in the state space, right, it was not a great loss, because with regard to the policy of learning how to navigate to R or how to navigate to Y, the features that I ignored were actually irrelevant, right. So, even though I could not make a distinction between whether the passenger is in the car or is at R while I am solving navigate, but that is only within the context of that navigate option or navigate subtask, and it is fine because the navigate subtask does not need it. But still in the global context we assume that we know exactly where the passenger is, we just chose to ignore it here, right. So, all of this is fine. So, now let us go back and talk about a robot navigation problem. So, if you think about any standard robot that is actually trying to navigate, what are the kind of features the robot will be getting. So, typically there is some kind of sonars all around it, and there are some bump sensors and things like that. So, it is possibly going to get some sonar readings, right. So, it will get like, okay, the nearest obstacle in that direction is 1 meter away, in this direction is 2.3 meters away, in that direction is some 0.8 meters away, and maybe there is an obstacle at the back or a wall at the back some 3 meters away or something like that. This is all the information it is going to get, right, and that is incredibly confusing to it, right. So, it will not be able to distinguish between, say, standing here, that there is a wall behind me, there is a wall in front of me and all of that, right, and then standing here, right. Possibly I am still getting the same kind of signals, I might send a sonar this way, sonar that way, right, and then say that, okay, there are openings on both sides, something is closed in front of me, something is closed behind me, right. So, that is basically all the information I am getting, right. So, it is not that I am choosing to ignore information here, right, it is just that the information is not even being measured, it is too expensive to measure. I need to put in a lot I mean much more sophisticated sensing equipment, so that is going to be more expensive, right. So I am not able to even sense enough information to tell me where I am. Think of another case where I could look around and let us say know everything, right. But suppose I am in one of those modern day office buildings which have a lot of cubicles in them, right. I turn on the robot, it looks around, it can see the cubicle, so it knows exactly where it is in the cubicle, right. But there is no way of knowing where the cubicle is with reference to the rest of the building, because all the cubicles look the same, right. Unless somebody has managed to put up some poster or something like that inside the cubicle, all the cubicles are going to look the same. So you look around, I know that I am in a cubicle, I know where I am in the cubicle, but I do not know which cubicle I am in until I start moving around, right. Or if I have a GPS coordinates and I know the exact GPS locations of all the cubicles, but that is another kind of sensor that I need to have, right. Okay, so think of humans, and we have been talking about robots so far, but think of animals, right. We suffer perceptual aliasing all the time. This is called perceptual aliasing. So I get the same perception, but from multiple different places, right. So it is like the perception is aliased, just like in signals, right. And humans suffer from perceptual aliasing all the time. So we continuously keep refining where we think we are, especially if you put you in this one of those confusing office buildings, right. So you keep walking around and then say, okay, now here I saw most things, most of us tend to anchor things to useful stuff like toilets and so on and so forth, right. Okay, so okay, now I saw that's where the men's toilet is. Okay, now I know where I am, so kind of thing. In fact, whenever I go to one of these big IT park like campuses, I invariably get lost. Okay, so unless there is somebody guiding you around, it is very hard to find your way around these buildings, right. They are built entirely to be characterless, right. So that all the buildings, so it makes it easy for you to shift companies, I suppose. All your offices look the same. Anyway, so this kind of, so what is happening here is some kind of partial information is available to you about the state, right. So I do not have the full information about the state, right. I only have partial information about the state. So we call this partial observability, right. So if you try typing in observability in any of your editors which does spell check, it will tell you it is not a word, right. But yeah, it's a technical term, right. So partial observability is essentially not having full information about the state space. Okay. So let's take a simple example. So for the time being, assume all the cells are of the same size, okay. So I do not want to erase and redraw, all the cells are of the same size. So an agent has a partial information, it can sense the following, okay. It can sense if, so suppose an agent is here, right, it can sense this square, this square, this square. So these are the 4 things it can sense, okay. Let us say it goes in this order. Okay. So, if all of them are clear, all the 4 places are clear, I am going to say, so 0, 0, 0, 0. That means there are no obstacles anywhere around me in my immediate vicinity, right. So, 0 means I can move in that direction without hitting into anything, right. So, for example, here it would be 0, 0, 0, 0, 0, 0, 0, 0, okay. And what about here?
1, 0, 0.
What about here?
0, 0, 1, 0, 0, 1, 0.
0, 0, 1, 0. Ah, okay. So we are going to run into problems with this, right? It looks like I have to erase something. Okay. Now we are going to have some fun. So is there any place that is 0, 0, 0, 0 here? No. Okay. So what about here?
0, 0, 0, 0, 0.
And here would be
1, 0, 1, 0.
so on and so forth, right? So there are, how many states do I have that? Is there anything else I have? I have a 0, 1, 0, 1. Anything else? 1, 0, 0, 1. Anything else? That's about it, right? Yeah. So good. Now can you give me a count of how many of each of these are there? 0, 0, 1 is where? That? Anywhere else? There's one more missing here. Yeah. Should be a 0, 1, 0, 1. Is there any other 0, 0, 1? No, okay, 1. Then 1, 0, 1, 0. Top and bottom.
1, 0, 1, 0.
0, 1, 0, 1. Left and right. 1, 0, 0, 1. Top and left.
1, 1, 1.
1, 1, 0, 0. Okay. So this is all the input that you will get. I'll get these 4 digits. So I'll get these four numbers, right? I'll get 0, 0, 1, 1 or something like that. That will be the input I get. Suppose I tell you that you are currently in state, that is observation that you have, right? Can you tell me where you are? I can be in any one of 4 places or 8 places. 8 places, right? So I could be here, 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 here and here, right? Now I'll tell you something. I am saying I am going north, right? I am telling I am going north. and what do I see next? I am seeing yeah, so where am I now? One of those 4 places, right? Right, because I saw 0 1 0 1, then I went up, I see 0 1 0 1 again, so I am in one of those 4 places. Now I go up again, right, and I see, I don't know, 1 0 0 1. So where was I earlier?
Yeah.
So this is where I am now, but in fact the only problem with this example is you don't need the history, that even without the history you can find out that you are here. That is why I tried drawing a more complicated grid, but then it became little too complicated, so I need to have something simpler. But the point is, you could see that as we keep more history around, right, our uncertainty about where we are, it comes down significantly, right. So in this case it turns out that this is a uniquely identifying observation. It could very well be that the sequence is uniquely identifying, even though the individual observations by themselves may not be uniquely identified, right. But in this case it turns out that the individual observation is uniquely identifying. So what is the takeaway lesson here?
Start state, if you have a bit of a trajectory. If you have a bit of a trajectory from that state onwards, you can identify.
Yeah, so the point here is that even though if you have partial observability, so one way of tackling the partial observability is to use some amount of history. Right, so one way of tackling this partial observability is to use some amount of history, and the history allows you to figure out where you are, right. So what really happened, if you think about it, is when you started out here, right, so I had some kind of a probability over where I am in the state space, right. I had some probability over where I am in the state space, and what was the probability distribution? It was 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 0 everywhere else. Then I moved, right, and then I made a updated distribution that had 1/4, 1/4, 1/4, 1/4. Okay, then I moved again, I made another updated distribution which basically has 1 here and 0 everywhere else, right. So what happens is, as I keep getting more and more observations, my belief about where I am in the state space keeps getting more and more focused, right. So this kind of this probability distribution that we maintained is called the belief state, right. So I have an MDP, the assumption we are making here is I have an MDP, right. So there is some state space below underneath it, right. So because we are now giving probability distributions to certain locations in state, right. So that means there is an underlying state space. So I am assuming there is an MDP with the underlying states and everything, right, but I am not able to observe the states of the MDP. I can only make observations which are some function of the state, right, and based on that I am going to form some kind of a belief about where I am in the state space, right, and I can try to do what? Yeah, but what do you do with it? What do you do with having a belief state? Can you use it to solve? Can you use it to get a policy? Huh?
You weight the policy with the probability.
So what are the things that you could do, right? So that's an interesting question to ask. So what I am going to talk about is for this class and the next class is different ways of solving partially observable problems. Okay, different ways of solving partially observable problems. So, a standard model that people use for this kind of partially observable problems is called a POMDP. So, you do not really need a POMDP. Okay, for some of the methods that we use, you really do not need a POMDP, but the POMDP is a good model to know, right. So, what is a POMDP? It is an MDP, right, plus some additional components for handling the partial observability. So, what are the things we are going to have? You are going to have S, you are going to have A, you are going to have P, you are going to have R. So, all of the standard MDP settings, and then you are going to have omega, which is a space of symbols, space of observations, right. So, for example, in this case omega would be, it will be 0 1 power 4, right, the set 0 1 power 4, or you could explicitly enumerate these things and say this is all my omega is, because I at least for this given world I can't see anything else, right. So, it is a smaller subset, half of it basically. Right. Instead of all possible 16 combinations, I have only 8 combinations that can occur in this world. You can obviously imagine a world where you could have obstacles in there, right, so that you get more of these combinations occurring and so on and so forth, right. So, that is my omega, and then I have my observation function that tells me something about how the states and the omega are related. So, essentially observation function is a mapping from states action omega to 0 1. So, it could be probabilistic. Okay. And so, it could be a function of the state and the action, right. So, one way of thinking about it is you can say if I am here and I move up, what will be the observation I will see. That kind of marginalizes over my next state distribution, right. Or you could also think of defining an observation function that says, okay, I am here, what is the observation I am going to see. What is the probability of 1 0 0 1 given that my state is this, which is 1. What is the probability of 1 0 0 1 given that my state is this, 0. That in this particular case we have assumed that the probability is 1 or 0, right. But in general I could have some noisy sensors. So, for example, if each one of my sensors has a small noise factor, right, they still report 0 or 1, okay, but they can report 0 or 1 with a noise of say 0.1, right. So, essentially, so 10% of the times if it is 0 it will report 1, if it is 1 it will report 0. Okay. Now, immediately my observation space has gone up to 60, it's 2 power 4, because anything can come on at any time, right. And then if I am here, what happens? So, the probability of 0 1 0 1 is only 0.9 power 4, right. So, there is a probability that I will actually see 0 0 0 1, right, which is 0.9 cubed into 0.1. Right, so, 3 of the things are reported correctly, 1 is incorrect. So, like that, so I can now start having probability distributions over my observations. Right, observations need not necessarily be exactly the same observations. Now, can we go back and do the thought exercise that we did? The simple exercise, not thought, I mean simple exercise that we did, right. So, I had 0 1 0 1. What would be my belief state? Does it only still have a support of 8? Doesn't, it's a lot more complicated. right? Those 8 states will still have the bulk of the probability because they will have 0.9 power 4. Is that right? Huh? Remember, Billy states should sum to? It can't be 0.9 power 4, right?
One would be 0.9 times 4. The exact opposite would be 1 minus 0.9.
No. What can be 0.9 by 4? 0.9 power 4?
All the states with 0101 will have 0.9 power 4, assuming that all the sensory measurements were right.
All the?
All the sensory measurements were right.
Into 1 by 8.
Okay.
Yeah, sum of all of them will be 0.9 by 4. Right, so I can get 0.9 by 4, I mean I can get 0101 if all the sensors are correct, right, with 0.9 by 4. And where will 0.9 power 4, where will all the sensors be correct is one of these things, right. But that is not the only places I can get 0101, I can get 0101 anywhere else also. In fact, I could get 0101 anywhere in the world, right, just that more and more sensors have to misfire, right. So what about here? Everything has to misfire, it is 0.1 power 4, right. So these places are the ones which I am least likely to be if I get 1010, right. Suppose I go here 0001, so what happens? One sensor is correct, the 0 sensor is correct, right. So it is 0.1 power 3 into 0.9, so the probability of me being there is pretty low. And now I moved up and I got 0101, now what do you think? It becomes even more weird because I will have to worry about where I was, and I am assuming now at least my motion is deterministic. And what if my motion is not deterministic? That is another confusion that you will have to worry about. I am assuming motion is deterministic, right. So if I had been here and moved up, right, I will be here, that is for sure, but I need to have been here. So what is the probability that I was here? That is what we just computed, right, 0.9 power 4 by 8. So with that probability I could be here, is it all?
No.
Huh? The new observations also could be noisy, right. So what is the probability that I am here and I actually make the 0101 observation? That is another 0.9 power 4, so I have to multiply by that 0.9, right. So it becomes more and more complicated, the computations become more and more complicated, right. So that is essentially one way we have to think about it. How will you do this belief update in a compact fashion? How will you do it? Huh?
Low probability.
What will be low probability?
Previous step has 0.9 to be power 4 by 8. The next step will be one of the 4 places
Yeah.
that.
See, one other thing
0.9
you
to
should
4 by
remember is me moving from here to here would be the other one, which is a high probability 0101 observation, right. But that will not happen because this has a low probability of actually having occurred initially. So what will happen is, earlier what happened, from 18, 18, 18 it became 1/4, 1/4, right. That will not happen now, but still these will be the 4 states that will have the highest probability.
The rest will get divided into.
It becomes more lower and lower. So in fact they will have much higher probability than what you started off with, distributing to the 8 states. So this will be closer to 1/4, 1/4, but will be discounted a little bit because you still have to give away a lot of things. So which will have high probabilities here, right. So the probability of you being here will be high, but this will be the highest, no question about it. These 4 will be the highest. Next up it will be this guy, because there is some probability that you could have been here and you moved up here, and this is the right observation to make here, right. And earlier you could have been here and you moved up, okay, the probability of this is very low, right. So those are the things that you will have to look at. So this, in fact, there will be an equal probability of you being here and here, because earlier the probability of you being here was low. So from a low probability place you come to a high probability place. In this case from a high probability place you go to a low probability place. So both cases the probability will be equally bad, right, but they will probably be the second highest probabilities among these states, right. So this will be highest, right, and then the second highest would be this. And everything else will have much lower probability, right. Of course the ones in the cross corridors would have almost vanished to 0 now. So we did 0.1 power 4 into another 0.1 power 4, it's gone there, right, that would have gone almost to 0. Now what about the third one? I go up again and I get 1001.
One of them will vanish to 0.
Which one will vanish?
The one where you had a good probability in the corner before,
Ah.
that will vanish to 0.
Which will vanish to 0?
So
This?
Yeah, that one. So in your second observation, that also had a probability.
Why will that vanish to 0?
Because you can't move up from there.
The second step is down.
the final.
No, but that is where I am now.
That is
No, so we calculated the probability of that being the second observed state.
Yeah.
So and we assigned and we said
No,
that,
at this point where am I was the question.
yeah. So for the previous observation, at this
I,
point,
well, if you want to go back and update the probability of where you were in the second step, yes, it will go to 0. But the probability of where I am right now, so that will be the highest probability, right? In fact, all other places the probability will start going down, but still they wouldn't have gone down to 0. It's only in the cross corridors they would have gone down to 0. In the vertical corridors, you will still have a non-zero probability of you being somewhere else. Right? So this should be familiar to people who are in the robotics class. How many of you are still around? 4. Okay, fine. So it should be familiar to you, all this belief state stuff, right? So we looked at it because it's used a lot in robot navigation, because that's the reality of things, right? So that's how things are with robots. So this kind of belief state computation is used a lot. Okay. So this is just to get you an appreciation of how hard it is. So we really need a compact way of updating the belief, right? So belief stuff sometimes written as that tells you that that's a belief that you are in the state S right now. It's basically the probability that you are occupying state S, right? That's basically the belief.